we shall start 10th lecture. This will continue discussion on nucleation treatment, single component system, solid liquid transformation. And if we see in the last lecture, we have found out this expression, and where this is critical nucleation barrier or activation energy, this is critical size, this is nucleation rate, where this term is taking care of taking the liquid atoms in the form of solid sphere to the top of that particular hill, and this part is taking care of the second event, where one liquid atom is added to the solid surface in order to make it stable. Now, this is the diffusion aspect what we have expressed, and this term is also called diffusional activation energy for liquid atom going to the solid surface. Now, if we try to see its evolution, so this is, let us say this is my solid surface and this is my liquid surface. Let us assume that they are having interface like this. Now, liquid atom, if liquid atom position is this and solid atom position is this. Now, this atom, let us say this solid atom position is vacant and this liquid atom takes the solid atom position. So, it cannot go like this. It always takes a path like this, which is governed by a kind of activation energy. So, this activation energy is nothing but delta GD. So, again this is also talking of some jump, and that time this would be the rate is proportional to exponential minus delta GD by kT, and this k is the Boltzmann constant. Boltzmann constant. Its value is 1.38 into 10 to the power minus 23 joule per Kelvin. So, now this particular term is sitting there because it talks about jump of liquid atom and going to the solid surface. Now, if we try to see the variation of R star and the variation of I, we can get some interesting information. Okay. Let us see that information in the form of graph. If I try to plot R star as a function of del t, so now if we see that R star is inversely proportional to del t, so that means R star would have a very high value and then gradually it will decrease like this. Okay, so this is R star variation. Now, if we try to plot I variation as a function of, this is I as a function of temperature, let us say this is my Tm, which is the melting temperature. At Tm, what would be the value of R star? So, now at Tm del T is 0, R star is infinite. Okay. So, now at the same time, if I try to plot, if I try to see del T G star value, okay, delta T 0, delta G star value would be very high. Okay. So, now another thing, if I try to plot at different temperature, what would be the variation of R star, we can also have a plot like that. For example, if I try to see the variation of delta G R as a function of R, you will see that that plot would be look like this. So, all will emit from this particular 0 point, and you will see that the R star is gradually increasing. Now, interestingly, we have to see what would be the temperature of those delta GR plot, because delta GR plot is at a particular temperature. Now, if I try to see that temperature, now as we see that R star is inversely proportional to del T, if we decrease the temperature, R star would decrease as we have seen in the last graph. So, that means as we are going from here to there, that suggests that delta T is small. That means we are going closer to melting temperature, and R star is also increasing. So, at Tm R star would go to infinite. So, that means smaller and smaller R value, that means the critical nucleus we are getting, if del T is more. This is interesting connotation, because we have seen from our normalizing and handling consideration, we have seen that if we increase cooling rate, increasing cooling rate means that we are taking del T more higher and higher. So, that means we can achieve del T, higher del T in the same time duration. Let us analyze that. For example, if I see the cooling rate, this is T and T, if I see the cooling rate is this and the cooling rate is this. So, this is cooling rate R1, this is cooling rate R2. If I try to see a particular temperature drop, okay, so that means within this particular temperature time duration, which is let us say del T1, and if I try to see this duration, which is del T2. Now, we are going by the same del T, but if the cooling rate is fast, we can achieve that del T much quicker than when the cooling rate is slow. So, that means in other way, let us say I fix my delta T1, let us say this one I have fixed. So, I would like to see in a similar time duration how much del T I can achieve. So, now if I go there, so here I am achieving this much, but here I am achieving this much. So, this del T is this one. If I try to follow the same duration, this much is the del T1 and this is delta T2, where in case of higher cooling rate. So, that means higher cooling rate gets me higher del T, that means higher undercooling. Now, if I get higher cooling rate, I am getting higher del T, that means my R star would also decrease. It suggests that I might get finer structure. Okay? The size of the sphere would be finer and finer, and I would get very, very fine structure. Okay? So, that also gives little idea that why increase in cooling rate during steel heat treatment gets me very, very fine pearlite. That means, or very fine grain size. That means, I am reducing the critical radius because of higher undercooling, and that is because of higher cooling rate. Okay. So, now this gives a little idea that yes, if we go for a higher cooling rate, higher undercooling, I would get very finer structures. Now, let us see the plot of I. Now, if I try to plot I have two parts. One is this part, one is this part. And interestingly, we did not mention this part. This I0 is a constant. Okay. This I0, the detailed expression of this I0 will be again covered by Professor Sangal. We will not talk detail about this. Our entire thing will be governed by how we can find out delta GV, and at the same time consequently how those expression would look like if we consider, if we take those delta GV value. Now, if we plot these two expressions, so let us write that two expression, exponential minus delta G star by kT, and the another one is exponential minus delta G d by kT. Okay. Now, I is common, I is common. Now, if I try to see this variation and if I try to see this variation, let us see how these two variations would look like in the temperature axis. Now, I am plotting first, I am plotting exponential minus delta G star by kT. Now, at t equal to Tm, so that means at t equal to Tm, would we get any R or the solid? Because at t equal to Tm, I do not have any undercooling. So, that means in order to get R, it has to be very, very large, which is not possible. Okay? So, it cannot go immediately to that particular big R. So, initially it will not be, there will not be any existence of this particular term. Now, as we are going lower and lower temperature and this particular nucleation event happens, that means going to the top of this particular peak, okay, it takes thermal fluctuation. So, that thermal fluctuation will not be sufficient to form a very large crystal or very large solid. So, that means we need a little undercooling. So, even if we have a sufficient undercooling, we will see that still the R star would be very large, still it is not possible. Okay. But at some point of time I would be able to see that the thermal fluctuation is able to give me a sufficient number of R star, okay, and which would be feasible and which we will be able to experience through this expression. So, now it would look like initially there will be nothing and then finally it will increase like this. Okay. So, till the point I do not see any expression, then any existence of this particular term, that means I do not have critical nucleus. Okay. So, now this particular section we call it undercooling, threshold undercooling. Threshold undercooling. Now, then if we consider the second term, exponential minus delta G d by kT. Now, as we increase temperature, I have more and more excitation of atoms. The atom can move easily. So, that means I must, this particular barrier term would decrease gradually with the increase in temperature. So, that times it would always increase, it is always increasing. Okay. So, now this is my exponential minus delta G d by kT and this is delta G star by kT exponential minus, fine. Now, what is R? What is I? I is combination of these two, the product of these two. So, the I would experience, I would be found out between these two lines. So, this is my I, which is I 0 kT. Now, before we go and do some calculations, let us see the practical existence of this threshold undercooling. Now, what does it mean, this threshold undercooling? Means that until unless we go till certain temperature range, down temperature, we cannot get rid of this surface energy, rather we would say that cannot supersede or exceed that surface energy contribution and make this delta G R term negative. Okay. So, then until unless this volume free energy term exceeds the value of surface free energy term, the nucleation is not possible. Now, this particular thing we see when we solidify pure metal, we try to see cooling curve of a solid liquid metal. If we try to see the cooling curve, that means the cooling curve is nothing but temperature time plot. If it is a pure metal, we sometimes see this kind of variation. So, the experiment is pretty simple. I have a furnace, and in the furnace you keep a liquid metal, and I put a thermocouple here and start measuring the temperature as we cool down the metal temperature, liquid metal temperature. As we cool down, we see that the melting point, at melting point, this is, if this is the melting point, it never solidifies at melting point. Rather, the temperature of the liquid drops to a certain extent before the solid starts appearing. Okay? And then once the solid starts appearing, it will go to, it will take a flat line till all the solid transforms, all the liquid transforms to solid, and it will be little below Tm, because at Tm it is all equilibrium. So, we cannot say the whether the transformation would take place or not. Equilibrium cannot be said to cannot be experienced. This phase transformation cannot be experienced at equilibrium point. We have to go little away from the equilibrium point. Okay. So, now that is why this particular thing has to occur little below the Tm, but if we see this drop, so that means the liquid temperature drops far below the melting point before the solid appears, and this happens because of the interface energy term. This interface energy, which is the positive contribution, does not allow the total system energy to go down the hill. Okay? So, that is why this particular thing we call it recalescence. Recalescence. So, this particular thing is nothing but this. Okay. So, now if we see that I variation, the I variation is like this. So, that means until unless we go little below the melting point, we cannot have any existence of nucleus. Okay. So, let us stop the discussion here, let us do some problem solving. So, then things will be very clear. Let us take a simple problem first, then we will solve a complicated problem. Calculate critical free energy of nucleation of ice from water, definitely, at minus 20 degrees Celsius, and where Tm is 0 degrees Celsius, delta Hm ice is equal to 6.02 kilojoule per mole, and gamma SL, which is ice water interface, is 0.076 joule per meter square. And also, while calculating this critical free energy, so we have to calculate delta G star. So, if I try to calculate delta G star, we need not delta Gm, rather we need delta Gv, which is delta Hm, delta T, Tm, Vm. So, now one data is missing, the Vm solid, that means ice, is equal to, or liquid, because we are considering that there is no volume difference when we go from liquid to solid, but actually it does not happen, because the liquid to solid, when it transforms, it has a positive volume expansion. So, that means solid, when solid forms, the volume expands, and because of this volume expansion, some interesting thing happens in liquid. Okay. If you have noticed, for example, if you can do one experiment. Let us say you take a small, you take water in a glass, open this one steel glass, take it to a refrigerator, freeze it, take that particular block out. Okay. So, let us say you have a glass and you have taken water, and let this thing to be taken into a refrigerator. So, that means you have now you form total ice. So, that means once you take the ice, so that means after that you take it out, try to wait for some few minutes, you will see that this ice becoming little free from this glass. So, then you take that ice out. So, this ice is taken out. Now, you put a wire around that and have little wet. You will see that gradually this wire will cut through the ice, but this particular ice block will not be separated into halves. Okay. So, this particular thing is coming from that volume expansion, also the pressure effect. So, we call it Clausius-Clapeyron effect, but we will not consider this particular Clausius-Clapeyron effect right now. When we talk about still heat treatment, it might come across, okay, the Clausius-Clapeyron effect. So, right now we are not considering, because our basic assumption while coming to this value was liquid to solid transformation does not have any volume change. So, this Vm is 19 meter centimeter cube per mole. This is per mole. So, now we can convert into meter cube. So, 19 into 10 to the power minus 6 meter cube per mole. Now, this one is 16 pi 3 gamma SL Q delta HM delta T TM this will be all square Vm square. This would be the expression, and now I just put those values 16 into 3.14 into 0.076 cube, 0 degree Celsius, that means 273 Kelvin, 273 square. Vm is this 19 into 10 to the power minus 6 square, 3 into 6.02 into 10 to the power 3, since it is kilojoule square, and here I am saying that minus 20 degree Celsius. So, my del T would be 20 degree. So, that means 20 Kelvin, this is square. So, now if you do this simple calculation, you would get 7.78 10 to the power minus 16 joule. So, this is the expression. Now, you can also find out R star, you can find out by 2 gamma SL by delta G HM delta T Tm Vm. So, it would be 2 into 0.076 into 273 into 19 into 10 to the power minus 6 divided by you can get R. So, that time this will be in meter. So, this is one simple example. We can calculate delta G star using that simple expression. Now, let us consider a bit a difficult problem. Now, that time I can write this delta G R term, which is 4 pi R q gamma S L, sorry, delta G V plus 4 pi R square gamma S L. Now, during that case, I need to find out the critical condition. We have seen the expression of the variation of delta G R, which is like this, where this is my surface energy term, this is the volume energy term, and this is my delta G R, and at critical point, which is this, delta G R becomes maximum and the slope becomes 0. So, that means unstable equilibrium, and that time I just find out what is the condition there. So, that means delta G R dr is basically my critical condition or the nucleation condition, critical nucleation condition, which would be minus 4 pi R square delta G V plus 4 into 2 pi R gamma S L. So, this case, so this becomes 0, the slope becomes 0. So, from there I can say that 4 pi R square delta G V by 4 into 2 pi R gamma S L equal to 1. Now, I have to convert it into this. So, in order to convert this, if I divide it by 3 and multiply with 3 and also I multiply with R, so this is R square. So, that time it becomes, so this 4, 2, so it becomes 2 by 3. Okay. So, now if I try to see the surface energy, is saying that surface energy to the volume energy term, it just reverses. So, these terms, surface energy is equal to 3 by 2. Okay, this is the answer. Okay, so let us stop here. We will go to the next topic in our next lecture. Thank you for listening. Thank you.